All right. So welcome back to another week. Remember to sign in the link below in the description, and also comment if you have any questions. So this week went over like momentum and collisions. So it's got like a couple practice problems just like every week. So I'm posting this a little late, or at least the answer is a little late. I was a little busy this weekend, so here we go. So a 10-kilogram block rests on a frictionless or a horizontal frictionless surface. A constant force of 20 newtons is applied for 5 seconds. What is the impulse? Okay, so A, what is the impulse? B, what is the change in momentum of the block? So we got 2 questions, 3 questions. What is the final speed of the block? Okay, so A, what is the impulse acting on the block? Well, what do we know about impulse? We know that impulse is just the force times the amount of time the force is being applied. That's the impulse, right? So if we draw out sort of what's going on, just to get a better visual, we have a block, 10-kilogram block, and we have a force that's being acted on this block of 20 newtons, okay? And this is happening for how long? 5 seconds. Cool. So we can calculate the impulse pretty easily. We just know that the impulse is 20 times 5 seconds. All right, and so that'll give us 100 newton seconds. Right. Cool. So that's our impulse. All right. So then B, what is B asking for? B is asking what is the change in momentum of this block? Okay. So what is the change in momentum of this block? Well, we know that the change in momentum is equal to the impulse, right? So our we know that our impulse is 100. It doesn't say 100. Well, let me this right. Our impulse is 100 newton seconds. Then that means our change in momentum is also going to be 100. 100, right? So yeah. So our change in momentum is going to be 100. Cool. Okay. So now that we have our change in momentum, we can find part C. So what is part C? So part C is essentially you want to find what the final speed of the block is. So if we know, we can find this final speed by using our momentum equation, right? So for example, we know that so P equals it's going to be mass times the final velocity minus the mass times the initial velocity, right? So that's going to be our change in momentum, right? That's going to be our change in momentum right there. So we have our change in momentum. We know that the initial velocity is 0 because it's the block is at rest, and then we have the mass. So then we can just find the final speed, right? And if we do a little simplification, we can make it look like this: minus initial. And then when we plug in our numbers, 100 equals 10 times velocity final minus 0, right? So then when you solve, we get a velocity of 10 meters per second, right? So our final speed of this block after we exert that 20 newtons of force is going to be 10 meters per second. Okay, so number 2, a force is applied to a 5-kilogram block to speed it up from rest to 20 meters per second in 4 seconds. A, what is the change in momentum of this object? B, what is the average force that was exerted on this object? So A. So we want to find the change in momentum of this object, right? So how do we find the change in momentum of this object? Well, we know change in momentum is just like mass times the change in velocity, right? So we can calculate that pretty easily because we know that it starts at rest and it goes at 20 meters per second. So the change in velocity is 20 meters per second, and the mass is 5 kilograms, right? So you just plug that in, 5 kilograms times 20, and that'll give us 100, right? So our change in momentum is 100 Newton seconds. So now for B, when we want to find the average force that is exerted on this object, there's two different ways we can do this. So the first way is we can use this equation where it's the force equal the change in momentum over the change in time, right? So if we do that, we know it's 100 is a change in momentum, Newton seconds, and then the change of time, it happened in 4 seconds, right? So when we do that, that gives us 25 newtons. Or what we could do is we could find the acceleration of this object and then plug that into the F equals ma equation, right? So this is what physics is all about, just making your own way to the answer. It could be multiple different ways, right? So acceleration we know is just the change in velocity over change in time. So in this case, we know the change of velocity is 20, we know the change in time is 4 seconds. So our acceleration is going to be 5 meters per second squared. And then when we plug this into F equals ma, right, F equals ma, we know that the mass of this object is 5, acceleration is 5, and that gives us 25 newtons. Right, so it comes out to the same answer. It's going to be 25 newtons. This is the average force being exerted on this object. All right. All right, number 3. So number 3, a 10-kilogram box slides on a horizontal frictionless surface at 8 meters per second. It strikes another 7-kilogram box at rest. What is the final speed of these two boxes that slide together after the collision? Right, so let's draw it out. Good visual. So I got a 10-kilogram box, 7-kilogram box. The 10-kilogram box is going towards the 7-kilogram box at 8 meters per second. And then, so this is the velocity of this guy, and the velocity of this one, it's at rest, right? So the 7-kilogram box is at rest. And then they come and they stick together, right? So the 10-kilogram box strikes the 7-kilogram box, and at the end, they stick together, right? So we have 10, 7. And then they move at some velocity over here, right? So that's what we want to find. We want to find the final velocity of these two boxes as they come, collide, and stick together. So this is what we call a perfectly inelastic collision, right? Perfectly inelastic collision. So it's perfectly inelastic because the two objects come and they stick together, right? It would be an elastic collision if they just bounced off of each other, right? And it would be inelastic if one embedded itself into the other. So it's a perfectly inelastic collision. So how do we solve this? Well, we know via the conservation of momentum equation, the momentum in the beginning is going to equal the momentum at the end, right? So let's calculate the individual momentums here. So the momentum in the beginning, we have mass 1, let's say that's a 10 kilogram object, and it is going at a certain velocity, plus the mass of the second object, and it's going at a certain velocity, which is 0. So that's going to cancel out. And then the final velocity, or sorry, the final momentum, we have mass 1, right, which is the 10 kilogram object. And then it is going to be going at a final velocity that is going to be equal to the mass 2, which is a 7 kilogram object, right? So these two velocities are going to be equal. So because of that, we can do some math, right? Factor out final velocities, and all of a sudden we have mass 1 plus mass 2, right? Now we have one unknown variable. So when we solve it, so this term is going to be 0, right? Because the velocity is 0 for the second mass, the 7 kilogram. So we know the momentum of the first one is a 10 kilogram object going at 8 meters per second. And then if you add the two masses together, that'll give us 17 kilograms. Then our final velocity is going to equal 4.71 meters per second. Cool. All right, number 4. So number 4, a 15 kilogram bullet traveling at 200 meters per second strikes a 3 kilogram block of wood. If the bullet remains embedded inside the block, how fast will the bullet and the block move together? Or if the bullet emerges from the block at 120 meters per second, how fast is the block of wood moving? And then assume there's no mass lost from the block. Okay, or the bullet. So for this one, part A, if the bullet remains embedded inside the block, how fast will the bullet and the block move together? Okay, so we got a diagram. Bullet, it's going this way, and it's going to hit a block of wood. This block of wood is 3 kilograms. Okay, so then when we know the bullet is traveling at 200 meters per second, right? And the bullet is 15 grams, which is 0.015 kilograms. So then what happens is the bullet gets embedded. So now we have some final velocity that we need to find. Okay, so we got an inelastic collision going on here, right? Because the bullet embeds itself into the block of wood. So again, just using sort of like the same as the last question, number 3, using the conservation of momentum equation. The momentum initial is going to equal the momentum in the final. And since the bullet embedded itself in the block of wood, it's going to have the same final velocity as the block of wood, right? So it makes it a lot easier. So then we have our equation, mass 1, V1, plus mass 2, V2, right? Equals, we know they both have the same final velocity. So our mass 1, let's say, is the bullet. So 0.015 times 200 meters per second. And then we know the block is at rest. So that's going to be 0. And that equals our final velocity. And then we just add the masses together, plus 3. And then when we solve this out, we'll get a final velocity of 0.995 meters per second. Right, so that is how fast our system is moving after the bullet embeds itself into the block. Okay, so let's go on to part B. So now for part B, the bullet emerges from the block. So it goes straight through the block, and now they both have different velocities. Okay, they both have different velocities after the bullet emerges. So this changes our equation slightly. So we know the final velocity for the bullet is 120, right? So if we just plug in all our similar, the same value, so m1 v1 plus m2 v2 equals, now it's m1 prime b1 prime plus m2 prime. I mean, the masses are going to be the same. The velocities will be different. So if we plug in our values, 5 times, so the initials are the same, right? 0, still 0. The mass of the bullet is the same, and it emerges at 120 meters per second. So now we have to find out what this 3 kilogram block, what that velocity is. All right, so when you solve it, you should get a velocity of 0.4 meters per second. Okay, so when the bullet goes through, passes through that block, assuming no mass is lost, the block will be moving at 0.4 meters per second, and the bullet will be moving at 120 meters per second. Cool. All right, so number 5. A force of 300 newtons is acting on a 2.5 meter long rod initially at rest, as shown in the picture below. So A, what is the torque acting on the rod? And then B, what is the angular momentum of the rod as the force acts on it for 8 seconds? So let's draw what's going on. 2.5 meter long rod. The force acting up on this rod, and the force is 300 newtons. Okay, so if we want to find the torque, right, so for part A, find the torque, we know that torque is the force times the radius, right? So in this case, the force is 300 newtons and the radius is 2.5 meters, right? So that'll give us a torque of 750 Newton meters. So now that we have the torque, that'll help us find our angular momentum in part B. So we know that our angular momentum, so the change in angular momentum equals torque times the change in time, so the amount of time that the torque is being applied. So we know our initial angular momentum, right? If we were to break this down a little bit, so final minus initial, our initial is 0. So that's 0, right? And then if we plug in our values, so 750, and we know it's being applied for 8 seconds. So then our final angular momentum is going to be 6,000. So that is our final angular momentum of this rod. All right, guys. Yeah, so let me know if you have any questions. Go ahead and comment below. If you have questions about the video, questions about anything in the class, I do have office hours still going on. Monday is Memorial Day, so we won't have office hours. So I believe I'm posting this on Monday. So yeah, just let me know. I think the final, 2-3 weeks away. So just let me know if you have any questions, any problems with the course. Comment below, sign in, do all that good stuff. Good luck on all your midterms or on all your finals. And again, if you have any questions, let me know.